right, here's what we're going to do on this page of the notes. What we're going to do is get a little bit of practice now with writing our own exponential equations or functions, right? We're going to write them ourselves based on some information given to us in a problem. These are going to sound like word problems, and that's because they are. In fact, even these may not look like your typical word problems, but I've got a good word problem for you on the next page of the notes, where based on the information given in the problem, you can write your own exponential function, which will then allow you to predict future events. So anyway, here's the way it's going to work. This is our general equation for an exponential function. You'll recognize most of it, right? This b to the x looks like an exponential function. But what we've got here is this a out front, which shouldn't surprise you. We talked about graphing exponential functions where you have a constant in front of the exponential function. That's all that a represents. Essentially, it's going to be our initial amount. So let me go ahead and highlight a couple of things for you here. As we go through these, we'll do a couple together and it should make really good sense. Y is always going to be the final amount. So that y, the variable y, will be the final amount. A is going to be the initial amount given. So A will be the initial amount. You should recognize that from when we used the exponential growth and exponential decay equations from the previous section, Chapter 7, Section 1. We did a couple of word problems with exponential decay and exponential growth equations, and we had an initial and a final amount. So same idea here. In the problem, x is always going to be the value that's associated with the y. All right, so here we go. Let's just jump right into one of these, and we'll show you how it works. Remember, we're going to be using our general formula, so I'll have y is equal to a b raised to the x power. So there we go, y equals a b raised to the x power. Now all I got to do is take the information that I'm given and figure out what goes where. Well, I told you that a is always the initial amount, right? The initial amount, and y is always going to be the final amount. Well, I take a look at the 2 points that are given, 0, 8, and 4, 2,048. Well, the initial amount is always going to be the one that goes with the 0, right? Because when x is 0, what is y? It's the initial amount. So this is going to be a. That means that my final amount is going to be 2,048. Makes sense? And I told you that the x is always going to be the value that's associated with the y. Well, my y is 2,048, so the 4 has to be my x. Hopefully, here's what you recognize. I now know a, x, and y, right? So I'll plug in for y, I'll plug in for a, I'll plug in for x, and the only thing I don't know is b. And that's what we're going to solve for. So let's go ahead and do that. 2,048 is equal to 8b raised to the 4th power. All right, here we go. I need to get this b to the 4th power by itself because I'm trying to solve for b. No problemo. Divide 8 to the other side, and what I wind up with is b to the 4th is equal to 2,048 divided by 8, which means b to the 4th is equal to, you do 2,048 divided by 8, I got a calculator right here, we'll do that real quick, you get 256. All right, let me come up here so you guys can see what I'm working on. I got b to the 4th is equal to 256, but I still got to get that b by itself. So let me rewrite it for you real quick. B to the 4th, 256. Now, how do I get that b by itself? Well, the b is raised to the 4th power, and we actually looked at this in the previous chapter. Back in chapter 6, we worked with radical functions, and we actually talked about how you solve these kinds of equations. They're radical equations because what I need to do is to get rid of the 4th power, I'll take a 4th root of both sides. So if I take a 4th root of a b to the 4th, as long as the index and the power are the same, they'll cancel each other out, I'll be left with a b. But algebra says whatever you do to one side, you got to do to both sides. So anyway, I take a 4th root of b to the 4th. I'm left with, sorry, not a 4, I'm left with a b. And the fourth root of 256 actually is 4. So now all you need to do is just write your equation, right? Because I do ask you to write an exponential function, and now I know what b is. So your exponential function will always have a y and an x in it. That's what makes it a function. It has to have an x and a y. So we're just going to plug in the b that we just found and the a that you were originally given. Y equals 8 times 4 to the x power. And that is your exponential function, right? I could easily graph this guy by choosing some domain values. We generally did -3 through +3. That would work just fine, right? To go ahead and graph this guy and take a look at your exponential function. Or at least it'd be a good place to start to set up your chart. Now, I didn't ask you to graph it, but you certainly could. I just asked you to write the exponential function. Let's go ahead and try another one, just to make sure you understand how this works or kind of get the idea of it. Again, I'm going to be using that general equation, y equals a times b to the x. Well, I need to figure out what my y, my a, and my x are. Remember, a is always the initial amount. It'll be with whatever the 0 is. So there's my 0, so that means 0.7 has to be my a. The y will be the final amount. Obviously, it's got to be the other point, so 3.5 will be my y. And the x is always associated with the y value. Since that's my y, 1/2 has to be my x. Let's go ahead and plug stuff in. I've got 3.5 for y. That's all equal to 0.7. And then I'll have b raised to the 1/2 power. All right, well, what I got to do is I got to solve for b. So I'm going to need to divide the 0.7 to the other side. So I'll have b to the 1/2 power is equal to 3.5 divided by 0.7, which means b to the 1/2 is equal to 3.5 divided by 0.7 is actually going to be a 5. Now, again, you should recognize this from the previous chapter. We know that anything raised to the 1/2 power, well, the 1/2 power simply represents a square root. So this actually is the square root of b is equal to 5. Let me come up here so you can see my work better. Square root of b is equal to 5. Well, in order to get the b by itself, we know from the previous chapter, in order to get rid of the square root, I just simply square both sides, right? Because algebra says whatever you do to one side, got to do to both sides. The square and the square root will cancel each other out. It'll leave me with a b, and 5 squared is 25. But I asked you to write an exponential function. I didn't ask you to find b. You have to find b to write the exponential function, but you're not quite done yet. My function has to have an x and a y in it. So y is equal to, my a was a 0.7, and then I'll have my b, which is a 25 raised to the x power. And that is your exponential function. Y equals 0.7 times the base 25 raised to the x power. So that's how you're going to write these exponential equations based on given some information to help you write the equation or the function. And now let's take a look at a problem where we have a scenario going on, a particular situation, a word problem, if you will. And I want you to write an exponential function for this bacteria culture. Okay, here we go. Here's what it says. It says Kristen starts an experiment with 7,500 cells. Hold up a second. Let's wait right there. It says starts 7,500 cells. Guess what that sounds like to me? That sounds like an initial amount, or our A, right? That's going to be A, our initial amount. After 4 hours, there are 23,000 bacteria cells. Well, that sounds like a final amount, which we said the final amount has to be Y. And the X will always be associated with the Y. Well, how long did it take us to get 23,000 cells? It took us 4 hours. So we just found our X. 4 hours has to be our X. Well, remember the way the equation, the general formula worked was Y equals a times b to the x. Let's go ahead and plug in what we know. Y, my final amount, is 23,000. That's all going to be equal to my initial amount, which is A, 7,500. I don't know what B is. We're going to need to find that. But it has to be raised to the X, which in this case is going to be a 4. Well, this will work the exact same way as the problems we just did. I'll need to divide the 7,500 to the other side. 23,000 divided by 7,500. I got a calculator here, and you do 23,000 divided by 7,500, and I get 3.066 repeating. In order to solve for b, I've got it's raised to the 4th power, and we actually saw this on the previous page of the notes here. In order to get rid of that 4th power, I just need to take a 4th root of both sides. As long as the index and the power are the same, they'll cancel each other out. And so I'm going to take the 4th root of 3.066 repeating, which comes out to be approximately 1.32. 1.32 is a decimal. If you're given decimals, I'll tell you about where to round in the problem. I didn't in this case, but that's all right. We're doing it together. If I ever have you do this on a test or a quiz, I'll let you know what you need to round to. Anyway, we've now found b, but please be very, very careful. I didn't ask you to solve for b. I asked you to write an exponential function. So we're actually not done yet. I need to take that value of b and now write a function, which has to have an x and a y in it. So y is equal to 7,500. My b is 1.32, and that's got to be raised to the x power. So there we go. What I now have is a function representing the growth of this bacteria culture. What I could do is take the function that we just wrote and graph it. And then based on that graph, I could predict how many bacteria cells I expect to be in the culture at any time, right? I could do it after 3 hours or 6 hours, 10 hours. We could do it 48 hours later, right? Now that I have a function, right, this guy right here, I can plug in any time I want to and figure out how big the bacteria culture is, how many bacteria cells I would expect to be present. All right, so this is a very, very powerful tool, being able to write an exponential function based on just a little bit of information, being given an initial value, a final value, and then writing your own function, which you can then use to predict the number of bacteria cells at any time. And again, we can do this for any problem. We could set up anything. A couple of examples I gave you were population growth. Remember, we did it for a basketball game. We could do it here. You could do it for interest, right? If you have an account where you're saving money and you get interest for that money, we could set up an exponential function for that as well. Lots and lots of different situations that this will apply, and we'll get a much more in-depth look at it in section 8 of chapter 7. So when we get to section 8, we'll do a lot more of this. All right, guys, what we'll do is on the next page of the notes, we'll take a look at the second objective, which is going to be solving exponential inequalities. So head on over to the next page of the notes. I'll meet you guys there.